Hello everyone, welcome back to Deviations. In this video, we are going to be covering differentials and linear approximations. So, in the last video, we talked about how we can use implicit differentiation in order to derive the derivatives of the inverse trigonometric functions. We're going to be switching gears a little bit, and we're going to start talking about differentials and linear approximations. We're only going to be talking about this for one video, but it's an important topic, just to round off our idea of what a derivative actually is. So, a linear approximation is what we are going to start with, and it should be mentioned, as I've always said, you should know how to differentiate functions in order to watch this video, just so that you know what I'm talking about here. Alright, so a linear approximation is basically how we're going to approximate a tangent line at a point, and we're approximating a function. So f of x is going to be approximately f of a plus f prime of a times x minus a. And we don't really want that squiggly equal sign, that approximation equal sign. We want a normal equal sign. So we're just going to make a new function. The linear approximation of f is going to be f of a plus f prime of a times x minus a. And this is really that approximation for the tangent line at a point. If I'm given a function like x squared and I want to find the linear approximation here, it's going to be the tangent line. So that's a linear approximation for the quadratic at that point. Alright, so now we're going to try out an example here. So we're going to try to find the linearization of an exponential function at a point. So let's find the linearization of 2 to the x at a equals 0. Before we plug in that formula that we just saw, what we are going to do is we're just going to take the derivative of 2 to the x. We need to make sure that we have everything that we're going to need in that formula. So f of x is 2 to the x. So that means that f prime of x will be 2 to the x times the natural logarithm of 2, if you remember some exponential differentiation from a couple videos back. Alright, so now what we can do is we can plug this into our linear approximation formula. That means that the linear approximation of f at a is going to be 2 to the a plus 2 to the a times the natural logarithm of 2 times x minus a. And now all that's left is to plug in 0. When we plug in 0, we're going to remember some of our pre-calculus exponential rules, and that's going to go to 1. That's going to go to 1. And that's going to go to 0. So what we are just going to do is we're going to simplify this, and that means that the linear approximation at 0 is just going to be 1 plus x natural logarithm of 2. Alright, and what's really happening here is we're finding that approximation for a tangent line at 0. So we have an exponential, and then we have our linear approximation right there. Alright, so now what we are going to do is we're going to switch gears and we're going to start talking about differentials. Alright, so a differential is really what we've been relying on for calculus. It's that infinitesimally small distance that allows us to get the exact slope of a line at a point on a curve. Alright, so let's talk about the differential. So the differential is that little change in x and y that we've been using to compute the derivative. And these look like dx and dy. And our slope, obviously, is dy over dx. Our y differential over our x differential. And there is a difference between dy and delta y that we've kind of been using when we've been proving the derivative. Also, it should be mentioned that while x and y are my variables now, maybe in physics I'll have dx and dt. Those will be my other differentials. Alright, so let's talk about what these actually look like. Let's say I have a graph. Alright, there's my graph, and I'm going to try to approximate the slope here. And this is not going to be to scale, because I want you to be able to see what I'm doing. So we're going to have a distance dx, and that's also going to be equal to delta x. And I'm also going to have a distance dy, and that's going to be the distance up to the curve. I'm also going to have a line here, which is our tangent line. And I'm going to have another distance, which is going to be up here. It's going to be delta y. So, as you can see, dy and delta y are different. And as we get closer to 0, as dx and dy get closer to 0, to these infinitesimally small values, we're going to get to a point where delta y is going to be very, very, very close to dy. Because as we get closer, our tangent line is going to get even closer to our curve here. Alright, so that's the idea behind a differential. Let's do an example. Maybe this will clear some things up. So let's compute dy and delta y for the function f of x is x cubed plus x squared minus 2x plus 1 on the interval 2, 2.05. So we need to find dy and delta y. So we're going to find delta y at 2 and delta y at 2.05. And we're going to subtract that, and that's going to give us delta y. So in order to find delta y, we just need to find our f values at both of these two inputs, and then we'll subtract them. So if f of 2 is 9, that's a simple calculation, and a less simple calculation, you might want a calculator. F of 2.05 is 9.717625. All right. And now we can compute delta y by subtracting these two. So f of 2.05 minus f of 2, that's going to be 0.717625. Great. Now let's find dy. So when we find dy, we need to multiply that by dx. So we're going to have dy equals 3x squared plus 2x minus 2 dx. And that's, of course, the derivative of our function up here, f. And now that we have this, we're going to compute this at the points. So our dx is going to be this minus this. So we can say that dy is equal to 12 plus 4 minus 2 times 0.05, and that is going to be 0.7. So that is the differential that we just found for this function between 2 and 2.05. And I could say we could maybe do this between 2 and 2.01. We'd get better and better and better. So that is how that works, and that was our example. So that was the linear approximations and differentials unit. So this was kind of diving a little bit past normal Calc 1 and Calc 2 topics, but it's good that we expand our knowledge. Next time we will be back to talk about exponential growth and decay, and after that we're going to be talking about maxima and minima of a graph. That's going to be exciting. We're going to see some real nice applications that we are going to get through calculus. Alright, thanks for watching. See you guys later.